Thank you, Hans. Good morning, good afternoon, good evening for everybody. It's a great pleasure to participate in this webinar together with Dr. Nikos, my the co-editor of this green book published by CIGRE and Springer. I'd like to thank Leonardo Energy and the Corporate Alliance for this invitation to present this webinar. This green book was the result of a project initiated by Dr. Nikos some years ago in CIGRE. So I'm with great pride as have acted as a co-editor of it. Next, please. For those of you that do not know CIGRE is the National Council on Large Electric System. It is headquartered in Paris. It's a major organization dedicated to the exchange of information and knowledge about large electrical power system. And the technical organization, CIGRE, is organized in 16 study committees dedicated to different parts of power system. And CIGRE also has national committees in almost 100 countries around the world. So it's a major organization dedicated to just to exchange information about electric power system. Specifically, this book, it is organized according to the 16 study committees that are grouped in 4 major classes. 3 committees dedicated to the equipment, 5 committees dedicated to subsystems, 6 committees dedicated to systems aspect of power system, and 2 committees dedicated to transverse technology like telecommunications and materials. So the chapters are organized according to this specific organization of CIGRE. Next, please, Hans. In this presentation, I will just introduce the main aspects of that are guiding the development of the future of electric power system, organized in 6 sections. So the main ones are generation, transmission, distribution, consumer aspects of technology, and also the storage and automation as common aspect of these major parts of power system. Next, please. So regarding generation system, I will just address the main aspect that are guiding the development of new technologies of a generation system related to hydro, wind, solar, and sea power. Next, please, Hans. So regarding hydropower, this is one of the most ancient forms of generation electricity. So the main development that we see today is the development of variable speed hydropower. This is an important development because it allows the turbine of hydropower to function in variable velocity speed so that it can be exported in the maximum efficiency of many parts of their operating curve. Of course, in many parts of the world, there are also underdeveloped many inversible binary pumped storage power plants that allows the turbine and also the pumping of water back to an upper dam so that you can store energy and reuse it later. 2 different arrangements are possible also for inversible power. This is the common known as inversible short circuit quaternary pumped storage power plant. This is a power plant with 2 axes, one for the pumping and another one for the turbining of water. And a different arrangement is possible also with what is called a ternary circuit, where both the pump and the turbine are mounted on the same axis. These are different aspects of the same concept of inversible storage power plant. Next, please. Another development that is already well known around the world is the wind power that is dominating most of the new developed and distributed energy. The main aspect of wind power is that they can be used at variable speed. And of course, one major issue for power plants is their volatility or intermittency. They usually use double-fed induction generators. This allows you to not only control the real and reactive power, but also to get the maximum efficiency and also providing ancillary service for the power plant. But the major aspect of wind power is their intermittency and the dependency they have on climate changes. Next, please. Another development that is also growing in power system is the solar power. Two versions now are being developed and used. The major one is the photovoltaic power, where you have also in large power plant with altitude and azimuth control to get the maximum efficiency so that you can guide the panel according to the position of the sun. Another possibility for using solar power is the thermal solar, where you concentrate with many reflectors the incidence of the rays on a thermal collector so that you can generate the thermal energy from the solar rays and use it also with altitude and azimuth control to get maximum efficiency. Next, please. Another development that is being experimented in many parts of the world is the sea power. Different mechanisms are possible for using the the waves. One of them is the sea wave power, where you have a specific bay to collect the temporarily the water from the forebay and use that bay to generate energy using, for example, water turbine. Another possibility is to have some floating pieces of floating on the wave so that you can use that floating movement just to compress gas or air in a chamber and use that compressed gas to move compressed gas turbine and to generate the energy. There are many possibilities with these two concepts. This is just two very common way to export sea power. The next, please. Regarding transmission system, I will just address briefly the issues related to transformers, reactors, the development of flexible transmission systems, multi-terminal direct current transmission that is perhaps in the very far future, direct current transformers and breakers, and advanced material and transmission line. Next, please. Regarding transformers reactor, the main current issues that is being researched today is the environmental restriction that are posed to transformer, mainly due to the noise and the use of oil and some chemicals that can danger the environment. Also, the loss of life time and mainly the impact of harmonics from converters that are being very common in today's power system. The future challenge is to develop new materials to be used in transformers and reactors, the development of new design software, and many new labs that are mounted in the world to develop new kind of transformers and reactors. Next, please. Uh, Regarding flexible transmission system, we have three, I'd like to mention just three very important developments that are taking place in the power system. The one related to flexible AC transmission system, where using thyristors and capacitor and reactors, you can control the flow and the voltage in the transmission line. Also, the concept of HVDC, high voltage direct current, where you can transform the AC power to DC power and transmit it to very far to very long distances. And of course, an important development related also to flexible transmission systems is the universal power flow controller, where using also direct control of converters, you can fine control the AC power that can flow in any part of the network. Uh, the advantages of HVDC are many. In addition to the maximum efficiency, you have also no stability limits. So this is a very important advantage. Less environmental issues because the transmission lines are more compact. We have fine power control. Also, it is possible to connect different systems with a synchronous frequency, and you have fine control of active and reactive power. Next, please. One important aspect of the future is the possibility of a multi-terminal HVDC grid. This is an important future development that is being researched mainly in China, and it's related to the use of many terminal HVDC grid, where many sources of DC power are connected to the same transmission system in DC. The main challenge to achieve this kind of grid is the development of a HVDC circuit breaker and also an HVDC transformer. And also there is a need for a synchronized central control for all the network. These are the main challenge for the development of a future multi-terminal HVDC grid. Next, please. Regarding these two challenges, the first one, the development of a direct current transformers, it's a major challenge for the implementation of the HVDC grid. One concept that can be used is to use two VSC converters together with a high frequency transformer just to lower or higher the voltage in a DC grid. And the second challenge is the development of direct current circuit breaker. This is an important, difficult challenge to be uh, achieved because you need to create an oscillating AC current just to interrupt a DC current. So the three main concepts that are being researched today for implementing as direct current circuit breaker is a hybrid circuit breaker where you have a mechanical switch together with an active circuit that can temporarily create by an external signal, an oscillating circuit in parallel with the mechanical switch so that you can interrupt the current. Another possibility is to have a passive resonance breaker as a parallel network with the mechanical switch can oscillate during the opening of the switch and create a condition for the interruption of the current. And a more advanced concept is just to get rid of the mechanical switch and just use a solid state circuit breaker. So these three concepts are being developed. Some of them are already in test in China, so that this is one of the possibilities for the future development of the HVDC mesh grid. Next, please, Hans. And finally, regarding transmission system, two major developments are related to advanced material for transmission line. Of course, the gas insulated line, GIL, is already being implemented in short transmission lines, and also in a near future, the superconductor line. The main challenge for these two are the need for a gas or liquid nitrogen return line together with the transmission line. So these are very expensive, but are very promising as new technology for the future. Next, Hans, please. Regarding distribution system, there are many new developments that are underway in the distribution system. I will just mention the advancement of the underground distribution system and the concept of microgrid and virtual power plants. Next, please. The concept of underground distribution is already well known, major in urban region and major city. The current development is toward the concept of very compact substation that you can have not only the transformation and switching inside a very compact case, but also all the sensors and communication and automation system embedded in this compact case. This is one of the concepts that is being developed because it can be delivered as fully mounted from the factory. Next, please. Another concept that is being developed in the transmission system, the concept of microgrid and virtual power plant. A microgrid or a virtual power plant is the joining of several sources of generation and consumption in a single concept and in a under a single control so that they can join the grid as a single power plant. The major challenge to implement this kind of solution is the decreasing short circuit they present due to the converters, the reversal of power flow that also presents some challenging for the grid, the requirement for fault right through during faults in the network. Uh, the great advantage is the optional possibility of off-grid operation so that a community can have a microgrid or virtual power plant disconnected from the grid. And of course, they offer the possibility of this community to participate in the market as a single entity. Next, please, Hans. Regarding storage, storage is one of the main challenges for the current state of the network due to the needs for reducing the investment in large transmission system. I just mentioned the developed in chemical and thermal storage, kinetic and gravitational storage, and also mechanical storage. Next, please. The most common form of storage is the chemical storage, major directed by the development of lithium battery, but also thermal storage is being experimented as a way to store energy in a thermal liquid, made water, uh, mostly for heating and other, but also for producing electricity. Next, please. Yes. Two very interesting concepts are being also developed regarding to storage of kinetic or gravitational storage. For kinetic storage, the concept involves the installation of a large flywheel in a very uh, compact case so that this flywheel is kept running, wheeling in high velocity in a vacuum space so that it can be reused after, mainly during emergency needs of power. This is a concept that is also can be static or it can be used in transport and other uh, use of electricity. Another concept is the gravitational storage, where a large piston is kept floating on a deep storage of water, and this piston is used to compress the water. During the storage cycle, you just move the water behind the under the piston, and when you need that energy back, you just return the water to the penstock to move a turbine. So it's a concept similar to a reversible hydropower, but contained just in a cylinder, uh, usually underground. Next, please. Another concept that is already being developed and is the concept of mechanical storage, usually a large container of compressed air, where you can compress the air when you need to storage and use that compressed air to generate electricity back. There are many installations in the world that are using this concept. Of course, it depends on a specific place to store the compressed air. Usually abandoned mines are used for that use. Next, please. I would like to mention also two important trends that are being observed in electricity consumption that related to the introduction of electric mobility and also the concept of residential automation. Next, please. Electromobility is being developed and used around the world, and there are many different ways to export electricity in the electrical car. I'll not get into detail in most of them. Just to mention that the common battery car is the most common for using electric mobility, but also many different hybrid possibility with hydrogen and supercapacitor or flywheel are possible. So this is a major movement in the electric mobility that is taking over all over the world. So this will also have a very strong impact on the development of power system, mainly because the battery in this electrical car can also be used to storage energy for the grid. So this is an important concept to be developed in the future. Next, please. Well, I think everybody is already aware of the advancement that are being taking place in home automation and residential automation. With the every home appliance today can be an intelligent device, so that many homes are being deployed with a home area network that connects all of these appliances, and this appliance can be controlled through the internet or directly from a utility control center through the residential gateway, so that now it's possible to directly control the functioning of many appliances. And this has not only many impact for the our homes, but also for the grid, as it allows the external control of many aspects of consumption in our homes. Next, please. Finally, I would like to mention the major developments that are taking place in automation related to telecommunications, substation automation, and of course, cybersecurity. Next, please, Hans. Regarding telecommunication, telecommunication itself is a huge space for new innovation, but the main aspect that related to power system is the standardization of all four levels of communication, from the field communication of real-time event bus to the substation communication to the enterprise communication and to the web and external to the corporation. These four levels of communication are already standardized by IC. The two major standards are IC 625 and IC SIM, the Common Information Model. So this is an important development because only two standards are needed for the full communication of within the power system and external to the electrical aspect, to the market aspect. The major challenge in the future is the harmonization of these two standards, so that a unique standard of communication will be possible in the future for the full electrical power system. Next, please. Well, regarding substation automation and power plant automation, currently the state of the art of automation is a distributed architecture where many functions are provided by different server that we call ID, Intelligent Electronic Device. This is the state of the art. Two central possibilities are seen in the future for the evolution of this architecture. One is the centralized architecture, where all major function of a substation can be performed just by one or two central servers in the substation. And the other possibility, the far future, is a cloud-based architecture where the full functionality of a substation or power plant could be run on the cloud. Of course, this is something that is very far from now, but the possibilities being developed mainly due to the introduction of the 5G technology that will possibly allow this development. Next, please. Of course, this full automation of substation and home automation introduced the possibility of attackers and open the possibility of hackers to explore the vulnerability of the power system. You can see 4 layers of possibility of attacks. The process hacker you can attack a substation inside a substation. The station hacker is also another possibility for attack. The corporate hacker, not only inside the corporate, but outside, and the external hacker. So the full automation of electrical power system has created a large attack surface, the possibility of a huge amount of hackers to attack the electrical power system. The high impact of this attack, because with the specific knowledge, it's possible to explore the fragility of the system. And of course, the solution is very complex because it involves a wide area exploration. Next, please. As a conclusion, I would like to mention the major aspect of development of the future electrical grid and some educational challenges that are facing today CIGRE and many organizations dedicated to this research. Next, please. So the traditional and current electrical network architecture is divided in 4 parts: the generation, transmission, distribution, consumer. This is usually allows just one-way flow of energy, and these 4 parts are segregated. Usually there are different companies that take care of this part. Next, please. The future development is seen as a mega super grid, where there is no distinction between distribution and transmission and generation. Of course, you have the possibility of the aggregation of many distributed resources, usually aggregated as virtual power plants and power cells, and also microgrids and nanogrids inside our homes. All of these functioning together in a super grid. The major challenges are the complex metering control, mainly how to provide a central control for this huge super grid, how to address the two-way flow of energy, the low inertia of this converted power source, and the low circuit power that introduced difficulties for the protection system. Next, please. As a solution and one way to address this problem, we suggest that in addition to the education in the traditional electrical, telecommunication, and automation engineering, we need to develop many experts in economics engineering and systems engineering, and mainly to develop new tools for management size to address all this complexity. Next, please. Okay, thank you for your attention. Of course, I'm available for any question you have. Thank you, Hans. Now I move the microphone to Dr. Nikos for the second part of this presentation.
Okay. Hello, everybody. Thank you very much. I'm very happy to be here and share this webinar with Ioni Patriota, the Square, who has been the one who really, thanks to his enthusiasm, this book came to become a book from the project that started in 2008. But now, with the help of all study committee chairs, this is now the green book of CIGRE for the electricity supply systems of the future. So I will cover in this part the system aspect. So in the next slide, you can see that I picked 4 topics because, of course, it's a huge area that cannot really be covered in the short time of half an hour. So I'm going to talk about power system development, power system operation and control, electricity market and regulation, about active distribution system and distributed energy resources. So as I said, this is of course part of the electric supply system of the future, CIGRE Technical Council book. So in the next slide, let's see the power system development economics, the current state and how things are developing. So let's, next slide, let's see that we have the 3 main components, which is generation planning, transmission, distribution. Generation planning, what normally happens is that now you have a lot of uncertainties, and you have multiple regions or subsystems. So in the past, or even today, the way the system was planned, the generation was planned, is through the equivalent load duration curve. That is a result of convolution of load and with outage and unit outage distributions. But this is not effective anymore because you have strongly correlated unit availabilities, such as solar and wind within a region that are subject to the same weather. So now you use state-of-the-art chronological simulations to optimization models involving uncertainties, like chance constraints models, risk-based models, robust models, and stochastic models. And these uncertainties impose huge computational burden on problem solving. Another component is that the generation planning now is in competitive or market frameworks. So now instead of minimizing costs, generation company aims to maximize profits. And system load emissions, instead of constraints, are now contractual values. So the price at which the company sells the energy to different kinds of customers and for different products and in different markets is depends on competition. So price forecasting for different kinds of energy becomes now a major determinant of generation and storage investment decisions. And finally, you have now to plan generation with flexible demand to have monetized reliability and externalities. So all this lead to formulations where you have a multi-objective planning problem. You have to monetize reliability, costs, environmental externalities, and even safety. And this imposes very explicit trade-offs and needs for monetization. So you require now very sophisticated price forecasting for hours with sufficient adequacy and also with insufficient adequacy. And the value of lost load, which is used to describe the per kilowatt hour cost of a blackout, is an important component that you have to take into account. Then let's move to the transmission planning. Similarly, transmission now traditionally it was based on avoiding equipment overloads in any contingency scenario. So you perform security analysis based on AC load flow, and then you have a master program that tries different reinforcements of equipment to automate the process and find the least cost reinforcements of the system which satisfy all security constraints. However, now the changes are high penetration of renewables, which make equipment overloads harder to identify. Equipment overloads might be cheaper to remedy by demand response rather than by reinforcements. And finally, with the international electricity trade, economic benefits from exchanges between different areas become economically more important than to avoid equipment overloads. So transmission planning has now become a value-based assessment, similar to generation. So you run security constrained economic dispatch with DC network approximations. And then based on the expected nodal price differences, you determine the value of additional transmission infrastructure between different nodes. So this is the value that together with the costs of this additional infrastructure determines based on the cost-benefit analysis of these constructions, you decide if you will propose the infrastructure to be agreed by the regulatory authority. And then the next point is that, well, yes, similar things happen in Europe, where you need chronological stochastic simulations over the wholesale market bidding zones to arrive at expected bidding zone price differences that determine the interconnection between the various European countries. And coming to distribution, distribution has been easier to plan. It's normally more radial. And let's see now that, next slide, that now you don't anymore only use simplified decision rules, but you use similar techniques like transmission. And next slide. Then you have tools to analyze the distribution networks with combination of reinforcement learnings. You evaluate unserved energy at wall and trade-off costs of reinforcement, losses, etc. And another more modern term is also to look the distributed energy resources like batteries, PVs, demand response, and how they can be used instead of network reinforcements. This is called non-wire alternatives. And another trend is that now the planning subproblems are more integrated. Transmission and distribution planning includes economic simulations. Also, generation and storage need network modeling because, of course, it depends on where they are located. The planning requires future generation capacities. Their transmission and distribution become more interrelated since DR and distribution also affects transmission. So ideally, you need a model that integrates all network, distribution, transmission, storage, demand, flexibility, etc. Such models are extremely difficult and extremely time-consuming to run. So there is a question if, given that different market players are responsible for different decisions, if such an integration of the model is necessary. And new needs and new research is now becoming, like new technologies are appearing, that's active distribution and big data, for a better, of course, modeling of distribution and load, modeling of DC, storage, new operation and control, climate protection, environmental constraints, multi-criteria trade-off, sector coupling is another area, stakeholder and citizen engagement, and planning revolution economics and energy markets with shifting rules of environmental and reliability constraints. Moving to the operation and control, here basically in the next slide you see that the system is working can appear in 5 operating states: in the normal state, alert state, emergency state, in extremis, and the restoration state. In each of these states, it can go through in different ways due to occurrence of severe contingency, and then to various types of control, emergency control, preventive control, restorative control, etc. Each of these states is characterized, next slide, by some satisfaction and validation and violations. For instance, the operating state, equality constraints, inequality constraints, security constraints are all balanced. In alert state, the security constraints are not satisfied, which means that in case of contingencies, the constraints are not satisfied by the available reserves. In emergency, both inequality constraints, which are the operating limits, and security constraints are not satisfied. And in restorative state, you have not the inequality constraints satisfied. So you moved from one state to the other through various controls. And if you look at the time scale where the various phenomena, next slide please, you see that they extend from long term, 2 to 5 years, to real-time operation up to 1 hour, coming to medium term, short-term, very short-term and real-time operation. And what is of high interest is a real-time operation in the next slide, where you have, of course, the primary, secondary, and tertiary control, where the various devices react, and you can also control at the secondary and tertiary level. And now what changes in the next slide is that you need, now you see that one basic characteristic of the future power system is the large penetration of power electronics interface devices, which now appear in all parts of the network, in generation, transmission, distribution, and loads. And they affect all types of stability, the rotor angle stability, the frequency stability, the voltage stability, and others. And you see here the 11 major concerns of the present operators, with the major concern of them being the decrease of inertia. So since you have increase of the inertia, your system is much more vulnerable to frequency distortions. And in the next graph, you see the effect of the amount of inertia. The inertia here is characterized as the energy stored in rotating masses, how the frequency behave after the loss of the generation, the same generation, taking into account also primary control and load reaction. So obviously the lower inertia you have the system, like 100 gigawatts, the higher is the transient of the frequency. That can, of course, activate relays and lead also to collapse. The next slide shows you that now you need new services. So you need synchronous inertial response. You need faster units and also synchronous condensers. You need fast frequency response at the primary control. You need dynamic reactive response. So this is for angular stability. You need ramping margins, now given in 1, 3, and 8 hour intervals. You need fast post-fault active power recovery to mitigate high rate of change of frequencies. Then you see in the ERCOT study that the needs for increased flexibility. Flexibility is becoming now very important. And since the thermal generators are withdrawn, you need to find flexibility in all levels of the system. Here you see how the flexibility, various levels of flexibility allow higher generation of higher wind power absorption in the system without curtailments. In this study, you see, for instance, with 100% flexibility or low flexibility, you can have a much higher penetration of wind with at the same curtail level. The next slide also shows you that we need also increased controllability, and this is now possible through the power electronics. You can enhance operation and network stability by synthetic inertia, grid forming controls. That's a very important also probability, very important functionality of the inverters. You can support system restoration, active and reactive control, power oscillation damping, etc. And next, a very important also new development is that you need enhanced cooperation between TSOs and between TSOs and DSOs. And this is again associated with the increased need for flexibility, since the thermal units that traditionally provide flexibility now are displaced by wind generators and less flexible units. Then you need to exploit the flexibility that exists at the distribution level, as we will see also later. So the enhanced TSO-DSO cooperation and coordination is much more important. Also for efficiency reasons, it's good that TSOs cooperate and enhance operational security. Also can share reserves for frequency management, congestion management, etc. The next slide shows you also another important development of sector coupling. Now you can see that networks like electricity, hydrogen systems, gas, heat network, cooling networks can be all coupled through energy conversion devices, and which is, power to gas, power to heat, and all these different conversion devices, and together with storage, not only electricity storage, also thermal storage and other forms of storage, liquid storage, can increase the flexibility of the system and can have a much more efficient system operation. So sector coupling is a very important new trend in various systems. The next slide, finally, the next slide will show you that control centers are also evolving. The modern control centers have much more challenges with forecasting, and also you see that now they are also transformed, as you see next, in distributed control centers. And you have phasor measurement units, PMUs with wide area monitoring systems to enhance awareness. And you see that you can have distributed energy resource management systems, like in Spain, they have a management system only to manage renewables, wind, large wind parks. And you see that the future solution for the distributed control centers at different control center models, and etc. So that let me now say a few things about markets and regulation. Markets are characterized by the how the markets are organized. We have markets how is balancing and settlement. We have gross dispatch and settlement, where energy is traded via the wholesale market. The market operator dispatches and settles all the energy traded, or net dispatch, where the markets only trade balancing amounts. Then another important issue is how you remunerate capacity in markets. So there are markets that only deal with energy and balancing services, other markets that have separate capacity remuneration. And then you have ancillary services, which is essential to maintain reliable supply. And there are different approaches. They can be incorporated in the market in conjunction with capacity and energy, or separately via tenders. They can even be imposed by regulatory requirements. And then you can see that distributed resources are again an important factor that changes markets. So some countries also effectively integrate distributed resources through aggregators. And yes, that's important. And then next is the market torsion. You have price caps that markets need theoretically to allow price to range from values that cause unnecessary generation to withdraw to values that will provide cost investments. And then subsidies, you have impact of such an investment in other competitive assets. They are normally used to help renewables to develop. And then there are two basic scenarios. Option one, which is a highly connected grid incorporating renewables at all levels, with pricing of their competitive prices, large-scale supplies for industry and large commercial operations. And then next slide, you can see that you have TSO-DUC operations. Global interconnections are important because between continents and regions to allow a more efficient exploitation of renewables. Common pricing across regions. These global interconnections, which are normally ultra-high voltage DC interconnection between continents and regions, what we call also super grid. This will provide common pricing across regions, harmonized regulatory frameworks, at wholesale level competitive dispatch, competitive markets, full reserve sharing, and larger grid to absorb renewables, at retail level efficient tariffs, because you will have efficient wholesale prices, and efficient mechanism for centralized supply, okay. And the next slide shows a picture of this transactive energy system, energy model, where you have the transmission system operator managing the larger grid, distribution system operators managing the local grids, and you have network operators that manage information flows between all participants, including markets, TSOs, DSOs, etc. And customers who can choose to buy, sell, or store their energy based on dynamic prices. And the second scenario is the loosely connected microgrids, where you have some conditions like you have expensive, next slide, you have expensive prices and abundant air availability. So central supplies are not so much needed. You have small generation developed. Local microgrids are developed at the town community scale with their own energy resources. You have a local operator managing the exchange in value and the operation of the grid at local level, and local markets, exchange energy capacity. And next, you can have also long-term supply arrangement between the local grids. And this is the future of the grid as seen at least by one company, ABB, which sees how the system was yesterday, today, and tomorrow, the large super grid, and the various local microgrids interfacing and providing a mixture of centralized and decentralized systems. And there is little time to cover my last slides, which are about distribution, distributed resources, and active distribution systems. And just to say a few words here, here you see that the three pillars are demand-side integration, storage systems, and dispersed and renewable generation. These are the pillars, and you see on top the various technologies and applications, multi-energy systems, DC systems, electric vehicles, smart cities, smart meters, smart homes, microgrids. And of course, there is a trend that now encourages, the next slide shows the drivers for these developments, which are the drivers for energy efficiency and cleaner environment, etc. And let's move to have a quick overview of the next slides. This shows their development, which are, of course, the various microgrids and virtual power plants, as Ioni described before, the power electronic interfaces, the battery energy systems that are very important and increasing their penetration. They can provide a large number of developments and large number of the benefits to the energy storage owner, like a wind park or something like load leveling, and to the system, the grid stabilization of the system, like peak saving, capacity firming, island mode, operation, slimless transition, spinning reserves, power quality, and frequency regulation. You can see also in the next slide similar effects you can have by demand-side management. Next slide. So with demand-side integration, electromobility, and smart metering, you can again have a number of benefits for the system. The next slide shows how the active distribution network impacts by the various, impacts all aspects, economic considerations, environment, and technical considerations. These are the way these sources, demand and generation, provide flexibility to the system, because now flexibility is more than distribution. That's why TSO, DSO collaboration is very important. You can see that what we said before about sector coupling, that also provides increased flexibility. And the applications that the benefits they provide. And similarly, in the next slide, the next move, you can see the microgrids and the virtual power plants, which are similar but different, because virtual power plants means you are at different levels. You can see that smart meters that provide today very important information to the customer and also allow you to have a distributed sensor system in your network. You see the development of the DC grids, not only HVDC, but also now low voltage and medium voltage DC. And in the next slide, you can see you need new methods and tools. You need to increase the hosting capacity by alternative solutions, like what we call smart solutions, like the ones I described before. And then, yeah, let's move. And you see now you have platforms to provide DSO-TSO interaction. So you see the microgrid and how it is controlled and how this interfaced with the transmission grid. And also you can see the development of platforms in the next slide that you can accumulate, you can aggregate all these technologies and provide the virtual power plant and aggregate DR. And this can be used by aggregators also to participate in the market. So this is really the developments of the distribution system. And you can see that in the future directions, look at the integrated energy systems, with electricity systems as the backbone. This is very important, the multi-energy systems I was saying, risk and weather assessment and mitigation measures, considered now in system planning and operation. That's a very important issue. Very few people look at the resilience today when they really plan the system. Seamless operation through fully interoperable and network subsystems, peer-to-peer transactions integrated with markets and electricity networks, and a number of specific issues, integrating increasing amounts of DR, etc. So, yeah. So I'm sorry I had to run, but there are so many things to discuss and time is really short. So I'm really, thank you for listening to me, and I'm available for any question.